Okay, guys, E2 elimination. We're looking at anti-periplanar requirement. Leaving group or tertiary carbon, strong base / nucleophile. We're doing E2 here. The leaving group and the H need to be anti-periplanar. That's highly preferred. And that's what we need to look for. That's not a sterically hindered base, so we're going to have no trouble abstracting the more sterically hindered hydrogen. It's going to be here, so we're going to put double bond here, which would be a tetra-substituted double bond. But the H and the bromine are the anti-periplanar, or trans-periplanar. We need to draw this in a Fisher projection. I'm sorry, not Fisher. Newman, circle, circle, dot, dot. Newman projection. Looking through here, did we look through here last time? Yeah. On the front carbon, we have a methyl straight down, a methyl. To the right, the bold is to the right. It's towards you guys, that's the ethyl. And the H is going back to the left. Looking through here, the H is going behind the wall. It's to my left. Okay, we look to the back carbon. We've got a T-butyl coming straight down. It's actually eclipsed with the methyl. Okay, we can draw it a little bit to the side. There's a methyl coming towards you guys. It's actually eclipsed with the front ethyl. That's another methyl. And then the bromine is going to the left. So as is, everything's eclipsed. Is this what we had drawn last Monday? Mm-hmm. The H and the bromine are syn-periplanar. Syn-coplanar. If you put a plane right here, the H and the bromine are on that plane, but they're both this way. We want to rotate. We want the H. That is the H we're eliminating, right? Yeah, it's the only one on these two carbons. I don't think we rotated anything last time. We ended here. Let's rotate the front 180 degrees. Let's put the H here. I'm rotating the front, and that's going to give the H here. Everything's rotating 180 degrees. The methyl is going to be here. And the ethyl is going to be here. That's just rotating the front. The back is the same. The back is bromine. Methyl. And what? T-butyl. So that's the same compound, just rotated. Now the bromine and the H are still in the same plane. Here's a plane of paper. But now they're opposite. They're anti-coplanar. And this is how it's going to eliminate. You can't see the two carbons there, but the double bond is going to be put between the two carbons. But at this point, importantly, these groups are on the same side. And these two groups, the two methyls are on the same side. So whenever you draw, you put your double bond in between the two carbons. The carbon on the left is going to have an ethyl and a methyl. Ethyl and a methyl. Carbon over here is going to have a T-butyl and a methyl. But the methyls are on the same side. And there's your product right there. Actually, because the T-butyl and the ethyl are on the same side, this is actually Z. Those are the two big groups. and we do not get E. E would actually be the more stable product, with the big groups being opposite, right? We don't get that because what rules here, what's very more important is the H and the bromine being amphicoplanar. That's always the most important thing of whatever we talk about. Questions about that? So we did not get the most thermodynamically stable product. We're doing E2. What if we were doing E1? Which product would we get? We would get this, but we would get E. Because E1 always gives what? E1 always gives the most stable product because E1 is not governed by anything other than thermodynamics. We may mention a little bit more about why, but that's just the basic take-home. E1 product. By the way, if you wanted to do an E1 here, what reagents would you use? Instead of KOH, isopropanol is just a solvent here. How would you do this E1? What would be the difference of the reagents that you use?
It's a weak base.
Okay, here.
A weak base.
A weak base, okay. What's a weak base?
Methanol. Water. Just without the KOH.
Yeah, if you just heated it on isopropanol, it would be E1 because, you know, E1 actually doesn't even require solvent. You can just heat this thing and it ionizes, and then the bromine acts as a base. Typically E1, you just kind of heat it in some inert solvent or a protic solvent. I mean, something like this could act as a base. As soon as you put it in a strong base, it's going to start going E2. Okay, next one. We got a tetrahydrocarbon with a leaving group. THF is just a solvent, tetrahydrofuran, common solvent, inert. Strong or weak?
Strong.
Strong. Sterically hindered?
Yes.
Yes, very sterically hindered. So, which product do you want to project here? What mechanism first off?
E2.
E2. Why E2? Why not SN2? Can you do SN2 on this carbon?
Yes.
That one we could not. Can you do it here though?
Yes.
Yes. Is this going to easily do SN2? No. Sterically hindered base is going to favor more elimination. Because taking the H is much easier than doing a backside attack. Now, which H are we going to take? There's two beta hydrogens. There's two types. There's HA here, and then there's HB. There's actually two there. If you take HA, we're going to get a trisubstituted alkene. If you take HB, you're going to get a disubstituted alkene. Which one do you want to take? Which one does the base? Take HB? Why HB? That's where it gets a little blurry, and sterically hindered keeps it from doing substitution, but doesn't keep it from taking that H. That's where it can get difficult. Certainly, if you wanted to take HB, which would be a better base, KOH or this guy? Yes. The more sterically hindered, the more prone it's going to take that H. But does that mean it's going to take it? That's where it gets a little blurry. sometimes the question may say, hey, show this HF product.
Also the H is being coplanar.
If we're asking for the HF product, which H are we taking? HA, yes. So show the HF product. Yes, the H, let's do both. Show both products. Show the HF and then we'll show the Hoffman. The H and the chlorine need to be what when the elimination takes place? Anticoplanar. Best way to see that is Newman projection. We'll look through there. I see a methyl coming straight down. There's the methyl. I see an H, HA going that way, and an ethyl going that way. Now on the second carbon, I see an ethyl coming straight down. I see a chlorine coming towards the right. And I see an H going back. We'll call that HX. Because I see students often get that H confused with this H and then get some funkified product. That H is not going to be abstracted, right? That's not a beta hydrogen. So let's X it out. The H is going to get abstracted is which one? HA. And as shown, it's syn coplanar. Syn is synonymous with cis. And the bold, both of them being bold, is sort of analogous to cis. We need to rotate it. We want the H over here. So if we can rotate the front, rotate the front, put HA here. Everything's rotating 180 degrees. They're going to be just the opposite. Methyl, and methyl moves up. Keep the back the same, chlorine, HX, and what do we got? Another ethyl? Two ethyls. Ethyl, ethyl. Okay, now we can rotate. Okay. I didn't draw it like that last time, but usually I do. That H and the Cl will eliminate, concerted elimination. The H and the Cl are anti or trans coplanar. And when it does, the two ethyls are on the same side and the H and the methyl on the other. So we're going to put the double bond in here. But these two ethyls are actually going to be on the same side. Whenever I race with the left hand, I'm reminded of how they do it in medical school. That's how they do it in medical school. So we have the double bond. The two ethyls are actually on the same side. And then the H, it's better just to look right here. Double bond is between the two carbons you can't see. Two ethyls are here and then a methyl. It doesn't matter where you put the methyl at because since these are the same, I can put it in either place. It's the same product. But the methyl and the HX, and there's your product. Double bond ends up between the two carbons. When ethyl's coming off. Between the two carbons, with these two ethyls, one there and one here, they're actually on the same side in the double bond, in the alkene. Okay, you can much easier see it from here. Once you get your H in the leaving group anti-periplanar, here are your two groups, one on the front carbon, the other on the back carbon. Methyl on the front carbon, H on the back carbon, HX. And once again, this is Z, because the two big groups are on the same side. So this is the Sasef, but it's the Z form of the Sasef. It's not actually the best form of the Sasef. Now if we do the Hoffman, we're taking the H over here. We call that HA. What is this, HB? So we're putting the double bond in here. We're going to have one end of the double bond, a methyl and an H. The other, we're going to have all this. Okay, here's a big thing here. Whenever there's two H's to choose from, there's two HBs. Whenever there's two to choose from, you don't have to do any of this looking at anti-periplanar. Because, what if there were two H's here on the front? Like an HA, another one. Well, which one would we put anti to the chlorine? What if there were two here? Like one here and one here. Which one would we put anti to the chlorine? You could put both. And if you can put both, then how do you decide? You're going to put the best. So it's going to do the best. It's going to eliminate to the best. And the best is the one that gives you the E, or the best product. So you don't have to worry about it. You're going to put double bond here, and you're going to have a methyl and an H. Okay, removing the HB, we're putting double bond in here. Coming off of this is going to be this whole group, but we're going to put it opposite the methyl, because that's going to be the best. We keep that stereochemistry because we do no chemistry here. So that stereochemistry remains. We're just doing chemistry right here. Where the base takes the H, electrons move in, that gets kicked off. But that H in the chlorine are anti-periplanar at the time. It's going to be E, and because it's the best. And there's your product. And this is called the Hoffman, yeah? Because we took the less accessible H. I'm sorry, the more accessible H. The more accessible H. Stereochemistry remains here. If you have two H's, you don't have to worry about doing any Newman or looking at how it's going to eliminate. Just show the best. Because you had a choice. Questions about either of those? Okay, triethylamine, TEA, is a sp3 nitrogen. Sterically hindered. It is strong enough to do an E2, although it's not an anion. It's not the strongest base possible, but it is strong enough to do E2. THF, just a common solvent. Oh, we have a ring here. We have beta hydrogen here. And we have actually two there. I'm going to call one HB and one HC. And they're not both bolded, because that would be very bad bonding. One is forward and one is back. Okay, if we want to make the SACEF product, which H do we remove?
HA.
HA. So let's look at that. Now I could draw this maybe a little bit. Either way, it's really supposed to be eclipse. I mean, the forward H is coming right in front of the back H. So either way, it's not going to look exactly right. Yes, put double bond in there, and we would have the alpha on the double bond. It would be the SACEF product. Okay, is this H and the leaving group, are they anti-periplanar? Anti is also trans. Are they trans-periplanar? Well, first off, are they trans? Are these two trans? No. And indeed, they're thus not trans-periplanar. Can these rotate and become trans? No, they're fixed in a ring. We cannot rotate these like we rotated the Newman. These will never be trans-coplanar or trans-periplanar. Of H, A, B, and C, is either any of these trans? Which one is trans? HC. It's the one that will get abstracted. Game over. There's only one choice here. Now you can eliminate cis-coplanar. These could eliminate if there was no anti-coplanar possible. But if there's an anti-coplanar, no matter what, that's the one that's going to come. This is going to take this H, these electrons move in, these get kicked off, and the product here will be double bond there. We still have that stereochemistry because nothing happened there. And which H is up here? This is now trigonal planar.
HA.
That's HB.
Oh.
And we can draw in HA if you want. I drew it in up there, so let's draw it in down here. HA. HC is abstracted. And there's your product. And that's just a disubstituted alkene. This is the Hoffman product. It's the product because there's only one H that can be anti-periplanar. Now, if we draw this in a chair conformation, we can see the anti-periplanar nature here. If I draw the iodine, first off, does the iodine have to be axial or equatorial?
Axial.
Axial. So if it's up, let's put the ethyl on the next carbon. How is it should be drawn? Straight down, because they're trans. That's up, this is down. If we're drawing the HA here, these are cis. Cis, cis. But is the H anti-periplanar to the iodine? No, the ethyl is. Iodine straight up, the ethyl straight down. The H is not anti-periplanar. Over here, there's two H's. The other beta one. You got a straight down bond and you got a equatorial. Which one do we draw straight down? Well, straight down would be trans to the iodine. Which one is trans to the iodine? HC. HB is here. These two are trans, right? Not only are they trans, they're also in the same plane. Now it's harder to see the plane here, but really the plane is in the, somewhat in the board. The iodine is straight up, that H is straight down. These are the two, of the H's drawn in, that's the only one that is trans-coplanar to the iodine. And the triethylamine takes this H, the electrons move in there, and kick that off, and you get the double bond in between here. So this is seeing it from the chair conformation, but it's pretty much all implied here. As you can see, the trans nature. And we talked about there's only an H, there's only a beta hydrogen anticoplanar if the iodine or the leaving group is axial. Look down below. Question there is which reaction would be faster? Any questions about this? Let's leave this up here maybe. Reaction would be faster. What's the difference? Same base, we're doing elimination. In both cases, we're eliminating an H here. It must be the one that's trans. I mean, that's no different. The difference is this group over here, which actually doesn't even participate. I mean, there's no change here. But here it's cis to the iodine, here's trans to the iodine. Elimination takes place here. Base, boom, put the double bond in here. Which would be faster? Bottom one? Why the bottom? Well, importantly here is, what position does the iodine need to be in when it eliminates? Axial or equatorial?
Axial.
Axial. Okay. Let's put it axial. Let's do this one first. When it's axial, how's the T-butyl? T-butyl would be over here. 1, 2, 3. They're cis, so the T-butyl would be what?
Axial.
Also axial. These are cis. This guy here, the iodine is axial. T-butyl is over here, but it would be what? I'm drawing the H's there. The trans. This would be equatorial. Look at this. Which one, this has to be axial to eliminate. Which one of these is more likely to exist like this? Top or bottom? Which one's going to exist like this? It's going to exist like this more often. Is this one going to exist like this, or is it going to want to do a ring flip? It's going to really want to do a ring flip, put both of these groups equatorial. So if we showed a ring flip with both equatorial, how would we draw the equilibrium lines? It would be heavily towards this, right? But up here, this one, is this one going to want to do a ring flip as much? No, so this is going to be sort of like, yeah, you do a ring flip and the iodine goes equatorial. Really the question here is, which starting material is going to exist in the needed conformation, ring conformation, to do this reaction? This one. This one is more often going to be in this conformation. Since it's more often in the required conformation, it's going to eliminate more often quicker. This one's going to be the fastest. Because the starting material is going to more often be in the required conformation. If you had a conformation where the iodine was just never going to be axial because all the other groups would have to also be axial or for some reason, then it's never going to be able to eliminate. But you can have just, you know, maybe this is only in the conformation 25% of the time versus this one is 50% of the time. You get that idea? Questions about that? What other elimination product could be formed in reaction A? Double bond up here, because you also have beta hydrogens up here. B and C. And yeah, double bond up there. You still have your T-butyl, no stereochemical change there. Double bond there. Those H's are the same, but if they were different, for example, if one was a deuterium or something, or if somehow they were distinguished, then you could write, but they're the same, so there's one of these H's remaining. In this case, they're both disubstituted. These are both disubstituted, so it's going to be hard to say which one is going to be favored. But for what I showed, you could still answer this question. Okay. Member Chair confirmations question.
Why can't B form that product also? Double bond in another location?
Why do you say it couldn't?
Unless it can.
What?
Can B form the same thing?
I think yes. I think I just said A, so just to focus you in on something. I don't see any reason why it couldn't. Can't remember what your specific question was, but reaction B would not give that product.
That's how I meant that.
What would be the difference? Reaction B would give the same product, but the stereochemistry would be different because it hits different stereochemistry to begin with. And nothing changed at that stereochemistry, at that chiral carbon. Okay. Rest of the way is some miscellaneous things, very important. Each topic is sort of miscellaneous. Okay, when either substitution or elimination is possible, which will occur? Recovering, substitution, and elimination reactions. And often we have to first say which is going to occur. We know if we have a very sterically hindered nucleophile / base, that elimination is going to be more favorable. What are some other things? Okay, here's one. Heat favors elimination. For example, if you take this alkyl bromide, you heat it in water, you get this elimination product plus HBr. And water really didn't do anything other than really just serve as a solvent. You can actually do this reaction without water, just heating the starting material. It's heat. On the other hand, okay, that's heat, delta, heat. On the other hand, if you do this at room temperature, you're more prone to get this substitution product. The bromine is replaced by the nucleophile. You also produce HBr. Heat tends to favor elimination. Why? Well, you already know this. If you look at your delta G equation, where's heat fall? Over here, temperature. Now delta can be used to denote a change, but delta is also used in like line reactions to denote heat. But here's your heat is listed as temperature here. Which term does the temperature magnify? H or S? Magnifies S, T delta S. It's multiplying S. What is S? Entropy. Temperature magnifies entropy. Okay, in which reaction is entropy more favored? Or more of a favorable attribute? The first one, if you get rid of water, which is just is nothing, it's a wash, okay? The bromide is becoming the alkene plus HBr. 1 is becoming 2. But down here, 2 is becoming 2. Down here, water's reacting. These two react to give these two. And which one is entropy favorable? Elimination. When you eliminate, you're breaking something apart. You're eliminating something. Okay? Entropy is favorable up there. If this is favorable, how do you make this even more favorable in the whole term? Temperature will magnify it. So the higher your temperature, the more it's going to magnify the favorable term. If you want to magnify your entropy, if you want to make it more relevant, throw in some more temperature. Increase the temperature. That'll make the entropy more relevant. Now that's drilling it down to numbers, but really the numbers ultimately tell you the answer here. We may not be drilling into why exactly, other than it influencing the entropy term. Heat favors elimination because of that right there. There's lots of reactions out there. You do it at, now you got to be careful because you say, well, heat. I know there's a certain reaction out there with alcohols. You do it at 100 degrees, it gives a substitution product. You do it at 180, it gives an elimination product. And I see students say, well, but that's heat. Yeah, but it ain't as much as heat as that. So in my example, I did room temperature and heat. That doesn't mean you can't have something like 100, you know. Substitution actually occurs here where higher temperature favors elimination. Because in this example, at room temperature, nothing happens. Because it takes, the substitution actually requires some heat because of like transition state energy and stuff. Okay, another miscellaneous thing. Involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. Look at these examples. If you take this alcohol and with HBr, you're going to get this. This is very much like the shaken, not stirred. We reacted with ACl. You got your T-amyl chloride, okay, acid-1 mechanism. Protonate, ionize, etc., etc. But if you do this same reaction but do HF, you actually get the elimination product as the main product. Why? Well, here the nucleophile is Br minus. Here the nucleophile would be F minus. What do you know about F minus being a nucleophile?
really bad.
It's a very bad nucleophile. That's why earlier on we used HF as acid when you want the anion to do nothing. F minus is a poor nucleophile. Poor nucleophile will favor elimination. And indeed it does, because you protonate, you ionize, and so you get to this cation. The F minus just doesn't tend to want to act as a nucleophile. Bromine will. Instead, which is a better base? F minus or Br minus? F minus is actually the better base, because when you say base, you're talking about taking H's. And when you talk about base, you're saying, okay, which one's more stable? Br minus or F minus?
S or BR.
Br minus, because it's larger, the charge is spread out. Okay? That's actually more stable. F minus is a better base. See, F minus is more prone to taking the H and the electrons moving in. Actually, I'm taking the wrong H, because that would be a Hoffman product. And I'm showing Saseb product, which is what you would get here, because this would be at E1. So no, you would not do that. Forget about that beta hydrogen. We take this one, and the H is moving here, and you get that alkene. Try substitute.
The first is the reaction right there at HBr.
Strong nucleophile?
Right.
Well, that's sort of borderline. It is an anion, and we said anions were strong. The problem is that's the conjugate base of a strong acid. So what do you know about the conjugate base of strong acids? You're weak. So you got to kind of know that that's.
But you don't do acid reactions with strong. Or well, it's weak.
And that's because it's actually borderline. You can actually do either here. It's a very gray area. A little bit, it can be confusing. We called it an anion strong. It is an anion. You should start with saying strong. But you got to recognize it. It's the conjugate base of a strong acid, so by definition, it's weak. So you got conflicts. You got conflicts there. So you got strong acid here. You can't have a strong base in front of a strong acid. Of course, nucleophile is different than base. It's very gray. But keep acid. Flat.
Does the hydroxyl group needs to be protonated before it leaves?
Always. That's why we're using HBr and not like sodium bromide.
And can we do this in the same step, like while the bromine detects that, the H protonated to the hydroxide?
Can you do SN2?
Like, can you do this coordinating and the BR tagging at the same time, or you have to first coordinate it and then in the same next step?
No, protonation of the OH is a single separate step. Better nucleophile, more prone to giving substitution. So this is an example of that, where this favors the substitution product, or down here you're more likely to get the elimination product. This idea can be applied to this reaction. A very common reaction of alcohols is to make the alkene. Forget about that. When you go from here to here, what's the difference in formula? This is missing what? What did we eliminate? We eliminated more than just the OH.
And an H.
We eliminated water. Because we eliminated the OH, but we also eliminated the NH here. That's the beta hydrogen. That was the leaving group. We eliminated water. When you eliminate water, it's called a dehydration reaction. We dehydrated the alcohol. It's a common reaction of alcohols. Dehydrate them to the alkene. This is commonly done with a strong acid like sulfuric. But importantly, not like HI. That's also a strong acid. But see, down here you have H plus and I minus. Where here you have H plus and HSO4 minus. They both supply the acid because we have to make that a better leaving group. Which is a better nucleophile, I minus or bisulfate minus?
I minus.
Better nucleophile is going to favor substitution. But if you want the alkene, if you just want to dehydrate, you use an acid that has a poor nucleophile associated with it. And we talked about this 6 weeks ago with choices of acid. So down here, you protonate, then you ionize, and you get to, and you know the old mechanism, you get the cation. I minus would add here as a nucleophile and give you a substitution product. But bisulfate, now you can draw out the Lewis structure. Usually I just let you do this. Will just act as a base. And these electrons move in here. You get this, and you reform your sulfuric acid. So the sulfuric acid is just catalyst. It's a common reaction of alcohols. Dehydrate them with a strong acid, but one that has a poor nucleophile associated with it. If you have a good nucleophile associated with the acid, you'll get substitution. Good nucleophiles prefer substitution. Poor nucleophiles prefer the elimination group. They'll just act as a base. Or really, water takes the H. Because this is aqueous, water takes the H. You really have H3O plus there. That's a common reaction of alcohols. This mechanism, of course, has to be what? We're eliminated by E1. Why is dehydration of an alcohol never E2? This could never be E2. Why?
Strong bases.
Because how do you make OH a better leaving group?
Strong bases.
Protonated with what?
Strong acid.
Okay, strong acid. E2 requires what?
Strong base.
Strong base. Huh. You cannot have strong acid and strong base at the same time together. Thus, E2 is impossible here. Okay, we'll end here. This is something we've already really stated. A more statically hindered base will favor elimination over substitution. It's already really stated there. But you can say, which is the best base for this reaction? Okay, hopefully at this point, obviously an elimination reaction, right? We're eliminating HBr, make the alkene. Okay, mechanistically, we're going to do some type of, well, it can actually eliminate by two different mechanisms. Which is the best base? Focus in on, okay, what mechanism, which base. Please be ready to do that next time. When's the test? Wednesday. I don't think we're quite ready for the test. That's we're going to delay it. I don't like having tests on Friday because of lab. We're going to delay it until next Monday. Any objections?
No. Not Monday.
Okay. We'll finish up everything on the substitution elimination on Wednesday, and we'll start some new material.